I think the current situation has been a blessing in disguise for the institute. I think the online mode of classes, which I think the institute wanted to start 2 years back. So necessity is the mother of invention. So I think the institute is now fully geared for online classes. They are even starting MTech. There are 3 MTech courses being started in online mode, sir, from next.
Okay.
From August 2021. The first one is going to be on artificial intelligence. The
Okay.
second one will be on business analytics and data science.
Okay.
And the third one is on communications and networking.
Oh, very good.
And all these will be in collaboration with corporate companies. Because
Oh, I see. Very good. That's a new venture. Yeah. Good.
So we are trying to ensure that there is no dilution because it's online. We're trying to make it equivalent to the offline version.
Okay.
So there are some challenges. So,
but admissions will be the same process or a different process?
Admission will be a different process. So the institute will be signing MOUs with several companies. For example, companies like Cisco, Amazon, Qualcomm, Texas Instruments, Flipkart, they have all come forward. So what will happen is each company will select 15 to 20 of their engineers.
Oh, I see. Okay.
The institute will interview them, select maybe 4 or 5 of them for the course.
Okay.
So to ensure that they have a good background and will be able to handle the rigor of the sessions here.
Okay, very good.
It's going to be a new experiment. It could be a failure. We don't know, but
yeah, we have to try these things. Yeah.
Yes. Professor Murthy, I want to know whether my audio is all right.
Perfect, sir. Perfect. This program is, the online program is for the employees of all these organizations, right?
Initially, that's what we are doing. So because we'll have some captive audience. And then after a couple of years, we'll throw it open to any professionals from the industries.
Okay.
Yeah. Only thing is, first 2 years scaling will be difficult because there is also a project involved. So I think in about 2 to 3 years time, idea is if we are able to figure out a way of handling the projects also in a scalable way, we will be able to throw it open to a larger number of professionals from the industry. And yes, so this will be a full-fledged 2-year MTech program, which can be completed in anywhere from 2 years to 4 years by the industry professionals.
Okay. Only concern that I have is with regard to mathematics.
Yes, so we want to have a rigorous selection process. Take only the people who are really good. And so we want to have an interview. We also want to have a programming test because that's also an important thing. So Professor Murthy, I will close the lecture around 9:20.
10:20.
10:20. I'll close the lecture around 10:20.
Perfect.
Yeah. Who will be the audience for this?
The students and faculty of engineering colleges. Mostly they are the stakeholders of BITES.
Correct. Is Professor DKS expected today?
Don't know. I think I had forwarded the mail to everybody.
Yes.
Jasma madam will start on time.
Okay.
Yes, sir. Yes, sir.
So about 221 participants are.
Oh, okay. How many are there right now?
221.
Oh, 221. Okay.
I expected to have around 300, 320.
Okay.
Because US was one of the most awaited lectures among the audience.
Okay. So let us see.
We have one lecture by Swami Manohar on Monday.
Oh, very nice.
And there's one more lecture coming up following week from Manish Gupta.
Okay. Very nice. So he's now the director of the Google Research Labs.
Correct.
So you're able to get very good people. I think it's good to get people from the industry also who are into research.
Yeah.
And, for example, Manish Gupta was IBM research director. Then he was also the director of Goldman Sachs. Then he was director of Xerox Research. Now director of Google Research Labs. And of course, Manohar is well known to all of us.
Yeah, correct. And we had lectures by Professor Vittal Rao.
Yes.
About 3 lectures, and then we had one lecture by Professor Balram.
Fantastic.
Then we had lecture by N.G. Subramaniam from TCS. And now 2 or 3 lectures by Professor Jamadagni.
Very nice.
One by Professor Jagadish.
Okay.
And we had one lecture by Sambit Sahu from Intel.
Okay. So almost you have a lecture once in 2 weeks or?
Every week almost.
Oh, you have a talk every week.
Every week almost. I think earlier the face-to-face was a bit difficult to manage, but now it's online is much easier.
Correct. I'll just come back in a minute.
Yes, sir. Just now, madam, we can start.
Sure, sir. Good morning. I'm Jasma Balasangameshwara from the Department of Computer Science and Technology, School of Engineering, Dayanand Sagar University. On behalf of Dayanand Sagar University and Board for IT Education Standards, it's my great honor to welcome our speaker, Professor Y. Narahari sir, the Dean, Division of Electrical, Electronics and Computer Sciences, and Professor of Computer Science and Automation, Indian Institute of Science, Bangalore. It is a great pleasure to welcome the delegates from various organizations. I heartily welcome the members of BITES and its associated institutions, and a warm welcome to my DSI colleagues, student leaders, and students. Professor Y. Narahari sir has been at the Indian Institute of Science since August 1979 as a B student of ECE department during 1979 to 82, ME student of Computer Science and Automation department during 1982 to 84, and a doctoral student of CSA during 1984 to 87. Since February 1988, Sir has been on the faculty of the Department of CSA and was chair of the department during January 2010 to July 2014. Sir is currently the Dean of EECS and the Professor of CSA at IISc since August 2014. During 1992, Sir was a postdoctoral researcher at the Laboratory for Information and Decision Systems, MIT Cambridge, and during 1997, Sir was a visiting scientist on sabbatical at the National Institute of Standards and Technology, Maryland. Sir is elected as a fellow of the following institutions: IEEE, Indian National Science Academy, Indian Academy of Sciences, Indian National Academy of Engineering, and National Academy of Sciences. In 2010 and 2015, Sir received the J.C. Bose National Fellowship from the Department of Science and Technology, Government of India. In 2009, Sir received the IISc Alumni Award for Research Excellence in Engineering at Indian Institute of Science. A brief about the lecture. Sir will be briefing on what game theory is and how it is a mathematical framework for modeling social situations and optimal decision making in a strategic setting. While game theory is concerned with analysis of games, mechanism design is concerned with design of games. So today's lecture basically focuses on applying game theory and mechanism design to research problems at the interface of computer science and economics, a very unique combination, in particular design of auctions and electronic markets, computational social science, online education, and digital agriculture. A warm welcome to you once again, sir. Over to you.
Thank you. Thank you very much. Good morning to everyone. Thank you very much for a very kind introduction. Thanks to BITES who are doing excellent work. And thanks to Professor Murthy for considering me for giving this talk. And I consider it an honor and a privilege to be giving this talk. This talk will be mostly at a high level of detail. I may not be able to get into technical details of game theory and mechanism design, but I will try to provide as many motivating examples as possible. Regarding the agenda for today's lecture, so as I already said, in the first part, I will try to present several motivating problems, which are all at the interface of computer science and economics. Algorithmic game theory is currently a topic which is being pursued in all the leading computer science departments in the world. And this is one area which has really grown in the last 25 years or so to become one of the contemporary and very hot topics in any computer science department. In the part 2 of this talk, I will be talking about game theory, some examples, maybe one or two definitions, and then I will try to bring out the notion of Nash equilibrium, which is easily the most fundamental notion in game theory. As it was already told, game theory is all about analyzing the equilibrium behavior of strategic games, whereas mechanism design is the reverse engineering of games. That is, it is the design of games to exhibit a desirable behavior. To give you a very simple example, I think the current Indian cricket team is an excellent example of game theory and mechanism design. They know how to analyze the behavior of the strategies and dynamics of the other team. And so they're very good in game theory. They're also very good in mechanism design because they're also able to come up with strategies with which they are now able to design a game in which the equilibrium outcome is a win for the Indian team. So I think please keep this at the backdrop of your mind. And then many of the notions and concepts in game theory will become fairly clear. So let me start with the leading trend in the last 20 to 25 years where game theory and computer science have come together. You would see that on the left side of this PowerPoint slide, you have all the legends in game theory and microeconomics. Many of them have actually won the Nobel Prizes. I do not want to, sort of name all of them. It's going to take some time. On the right side of this, we have legends in computer science, many of whom have actually won the Turing Award, which is the highest prize in computer science. And what has happened over the last 20 to 25 years is a marriage of game theory with computer science. And it all started in the 1920s. So on the top left, we have von Neumann. He is widely regarded as the father of game theory. So in 1920s, von Neumann and Oscar Morgenstern, a leading economist of those times, they were at the Center for Advanced Study in Princeton, and they were actually laying the foundations of game theory during those days. And there was a fantastic collaboration between the two legends for 16 years, between 1928 to 1944, during which I think all the fundamental notions underlying game theory were formulated by them. And they actually came up with a 1,000-page book, the theory of games and economic behavior, which to this day continues to be the most authentic source of all the fundamental results in game theory of those days. And one of the most remarkable aspects of von Neumann was that in the 1930s, he was actually the one who formulated the notion of an algorithm, the notion of complexity of an algorithm. So in some sense, he was making fundamental contributions to computer science. So imagine, a legendary scientist, mathematician, making, leading contributions to game theory and computer science in the 1920s and 1930s. And then 60 years later, there is a confluence of these two disciplines to lead to the birth of algorithmic game theory. So you can imagine the vision of von Neumann during the 1920s and 1930s. What has happened is that the discipline of game theory and mechanism design now has come to be applied to a wide variety of contemporary situations. I will first try to give a few generic examples to you, and then I will try to give more specific examples later on, including some of the examples that we are currently working on. Let me start with this example of cake cutting that all of us know very well. Here is a mother. We call her the social planner in the family. We also call her mechanism designer. She's the one who designs the mechanism or who designs the game. And then you have two kids, 1 and 2. In game theoretic terms, we say that these two kids are rational and intelligent. I'm going to use these two terms, rational and intelligent, fairly frequently during this talk. The meaning of rational is that you are always trying to choose a strategy which is going to maximize your own utility function. You always have a utility function. You want to derive maximum benefit from the actions, and then you always want to maximize your own utility function. So rationality basically is maximization of expected utility. Whereas intelligence means that, you have enough, amount of computational resources and also intellectual resources to be able to find out what is going to happen to the dynamics of the game over a period of time. So you are able to imagine the consequences of your actions and the consequences of the actions of the other players in the context of your actions. So you're able to come up with strategies or optimal strategies to play in the game. So when we talk about game theory, we always assume that the players there are rational and intelligent, and we will try to see how the strategic play among the various players will unfold. So in this example, the cake has to be divided equally between kid 1 and kid 2. But the problem here is that even if the mother takes the best knife in the world and sort of slices the cake into exactly 2 halves, then each kid will get 1/2 of the cake, but each kid will have the feeling that the slice that she has got is the smaller of the 2 slices. So the kids will never be happy, come what may. So to appreciate this very well, imagine that kid 1 is the Karnataka state government and kid 2 is the Tamil Nadu state government, and the mother here is Narendra Modi, our prime minister, and then the cake in between them is Kaveri waters. Now, whatever strategy, whatever distribution policy that Mr. Narendra Modi comes up with, I don't think either Karnataka or Tamil Nadu will be happy with that. So the question is, can we design a mechanism? This is a game that is happening between kid 1 and kid 2. Can we now design a game so that both the kids are kept equally happy? So I will not give the solution right now. I will give the solution when we come to mechanism design. Now, the second example that I would like to take is an auction for selling an item. Imagine that there is a single seller and there are 4 buyers, and then there is an item, there is a very valuable item that the seller would like to sell to these 4 buyers. There is only one item, so only one of them will get it. So the most common way in which this is done is to ask the buyers to bid. So imagine that player 1 has bid 40 rupees, 45 rupees, 60 rupees, and 80 rupees. These are the bids. These may not be just 40 rupees, 45 rupees. This could be $40 billion or $45 billion if you're considering spectrum auctions, for example. So this could be very, very heavy amounts. And now here is a situation where we would like to, the seller would like to maximize the profit. At the same time, the buyers also would like to go away with the feeling that their utility is also maximized. So you would like to keep the seller and also the buyer very happy. So one simple way in which you can do is to award the item to the person who has bid the highest, in this case, the person 4 who has bid 80 rupees. And then this person will pay 80 rupees to the seller. But it turns out that such an auction does not have very desirable results. Now, if you want to maximize the utility of both the seller and the buyer, it turns out that you have to tweak this auction in a very simple way. What is the tweaking that you have to do? Award the item to the highest bidder, namely bidder 4, but the bidder 4 will not pay 80 rupees, but will pay 60 rupees, which is the second highest bid or the highest losing bid. And Professor William Vickrey in the 1950s and in the 1960s did remarkable work in this area and showed that such a second highest bid auction, which is also called the second prize auction, satisfies extremely desirable properties and keeps both the sellers and buyers happy. Now, you can also imagine a reverse situation where instead of a seller trying to sell, there's a buyer who is going to buy, and there are multiple sellers. This is something that happens routinely in the procurement of various things that we do, that institutions or organizations or companies will do. And similarly, here again, if you want to design a mechanism or an auction which will satisfy both the buyers and sellers, here again, you can go for a second prize auction. And again, William Vickrey's Nobel Prize winning auction comes into picture here. So as my next example, let me look at matching markets. Now, in the previous two cases, when you had an auction, we had one single seller and multiple buyers, or one single buyer and multiple sellers. But here, if you have multiple buyers and multiple sellers, it becomes a market mechanism. And matching markets are extremely important, and they are being used almost everywhere. So for example, the matching market could involve students and colleges, it could employ employees and companies, doctors and hospitals, and agricultural farmers and the people who consume the agricultural produce. So if you want to design a matching market that would maximize the social welfare here, and also induce honest behavior from all the stakeholders in this particular matching market, then it turns out that game theory and mechanism design have a very important scientific role to play in the design of such markets. So I have provided to you several generic examples. Let me look at some very concrete examples. I will not have too much of time to get into the details of these examples, but let me try to give you a feel or a flavor of these examples. So I call these societal examples. So for example, let's say we want to design massively open online courses in a way that it is good for the instructors who are offering these courses, and it's also good for the very large number of students who are taking these courses. So what we want to do is we want to improve the participation level and involvement of students and instructors in an online setting. So it turns out that if you are able to design the incentives for the instructors and the students in the best possible way, then all the problems which are currently there with MOOCs, for example, lack of hands-on learning, then student ratios, dropouts, and so on. So many of these issues can be effectively solved in a very scientific way if you are able to apply game theory and mechanism design to this particular problem. So you are able to design, design high performance online educational platforms using principles of game theory and mechanism design. Now, I would like to give an example of something very recent that has been done in IISc by Professor Rajesh Sundaresan and his group. They have actually come up with a very nice incentive mechanism. They actually used mechanism design to solve this problem. So what is this idea here? The idea is that, during the COVID pandemic, when the pandemic was somewhat on the wane, many organizations and companies and institutions were trying to open up. But the government had to take a decision which organizations to open up, which organizations not to open up, based on the preparedness of these organizations. So now, how does the government judge the preparedness of these organizations? So what they would do is they would give them a questionnaire, and then based on the responses to the questionnaire which are given by the organizations and companies and the various measures they have in place for taking care of the pandemic, then the government will either say yes or no. Now, if the government has to say yes or no in a scientific way, then it is very important that the responses which are given by these organizations or companies are truthful and honest. So if you want to elicit honest, replies from all these organizations, then what kind of incentives can you give to these companies or organizations is a very important question. And this question was effectively solved by Professor Rajesh Sundaresan and his group in IISc, and this was actually implemented by the government of India. So you can see game theory and mechanism design in action in real world contemporary situations. Now, I will now give 2 or 3 examples in digital agriculture, where game theory and mechanism design can play a very important role. And these are some problems that our own lab, game theory lab, is currently trying to work on. So you would see that farmers suffer tremendous losses due to poor choice of crops. Now, data science techniques where data is available, and you have to use game theory and mechanism design also in order to recommend the best portfolio of crops. So what you are basically trying to do here is to tell the farmers in the next 6 months, this is the combination of crops that you can grow in your agricultural land. And so we are actually trying to use a sophisticated mathematical model for that, a combinatorial multi-armed bandit problem, which again uses mechanism design. And you are now able to come up with an optimal recommendation to the farmers. And if the farmers are able to follow these recommendations, then it is going to be good win-win for the farmers. This is the crop recommendation engine. Now, the other example I have is a trading agent for farmers. Now, it is very important for the farmers to know what kind of prices are going to be possible for whatever agricultural produce they are going to be producing in the next 2 months. It will depend on a variety of factors. It depends on climate. It depends on cost of cultivation. And it depends on so many other factors, and data on historical aspects is typically available. But now what we want to do is we want to be able to predict these prices very accurately to help out the farmers. So there you can actually use some machine learning techniques combined with mechanism design. And then when the farmers have harvested the crops, and now they want to get the best prices for them. So now in many cases, it turns out that the farmers have to, sort of participate in some auctions and so on. So we can actually design a trading agent or an auction agent using principles of game theory and mechanism design. And this trading agent actually will do the bidding on behalf of the farmers. It's very difficult for the farmers to know all the intricacies involved in trading and bidding, but you can actually design a trading agent which will do the bidding on behalf of the farmers and ensure that the farmers will get the best possible prices. The last example that I want to give is in cooperative farming. So there are what are called as FPOs, farmer producer organizations, where multiple farmers will come together and they try to do things together. And if you want to ensure the success of farmer producer organizations, we have found that some of the principles of cooperative game theory can be used in a very scientific way to help farmers to plan their cooperation with the other farmers. So I have now tried to give you both generic and specific examples of where game theory and mechanism design could be used. So I will now go to the second part of my talk. And before going to the second part of the talk, let me summarize what the intellectual challenge here is. Now, all the problems that we have looked at so far, they involve strategic agents. All the stakeholders there, buyers, sellers, everybody there, they're all strategic. They're all rational and intelligent. They want to maximize their own utilities. In some sense, they're self-interested. But if everybody is self-interested, then the dynamics among them could result in an outcome which is a very poor social outcome. And these agents can also manipulate the algorithms and solutions that we're using in many different innovative ways. So the central question that we would like to address is, how do we realize social goals? So how do we maximize social good in the presence of self-interested agents? How do we make the agents to behave honestly? So how do we induce honest behavior from all the self-interested agents is a very important question that underlies all of these problems. Now, turns out that game theory and mechanism design have very scientific answers to these challenges, and they're able to fill this very important gap in trying to dealing with the strategic behavior of all the stakeholders. So that is the challenge that game theory and mechanism design are able to address in a very principled way. Okay, so let us go to the second part of my talk, where I will try to introduce to you some very simple notions of game theory. So for this, I have already told you that von Neumann and Oscar Morgenstern are the ones who are widely regarded as the founders of game theory. This was in the 1920s, then they came up with several formulations of games. Let me define for you the simplest form of such a game. This is called as a strategic form game. In a strategic form game, there are n players. N equals 1, 2, ... little n. So there are n players. Each player has a strategy set. Call these strategy sets as S1, so on, Sn. And then each one of the players also has a payoff function or the utility function. As I already said, every player would like to maximize an expected value of this utility function. Let me give you an example of this. This is the first example that I give in my game theory class. There are two students, A and B, who are both students of IISc. They're good friends, and they have two strategies that they're supposed to choose from. Either they can be in IISc or they can go to MG Road. All of you know about MG Road. Those of you who do not know about MG Road, it is called Mahatma Gandhi Road. But all activities, none of the activities that happen in the MG Road, or all the activities that happen on MG Road, have nothing to do with Mahatma Gandhi ji. Mahatma Gandhi ji will be extremely sorry to see the kind of activities that go on MG Road. But however, these IISc students would like to be there on MG Road also. So here, because these are two friends, now, if they are together, then there is a certain happiness that they are able to derive out of it. So that is their utility in some sense. We are now representing these utilities in terms of these numbers here. These are real numbers. In this case, it happens to be just integers to make it simple. So what's the game here? The game here is the following. These two students do not know what the other student is going to decide. They will have to decide on their strategy, namely IISc or MG Road, simultaneously. It's a simultaneous move game. So student A does not know what student B has decided, and student B does not know what student A is going to decide. They will have to decide simultaneously. All that they know is that if both of them are going to be in IISc, it's very nice because they can go to the library, do a lot of studies, and then both of them will get a utility of 100, 100. Whereas if player A is in IISc, player B is in MG Road, because they are not together, they are deriving a utility of 0, 0. And that is the case in the other symmetric case where player A is in MG Road and player B is in IISc, 0, 0. Whereas if both of them are in MG Road, the utility that they are going to get is 10, 10, which is of course much less than 100, 100. So this is called as the payoff matrix. Now, both the players know this payoff matrix. It's actually common knowledge, meaning both the players know this payoff matrix. Both the players know that both the players know the payoff matrix. Not only that, both the players know that both the players know that both the players know this payoff matrix. This is called common knowledge. So under these assumptions, we would like to know what the players are going to decide, and then rational and intelligent players will play strategies according to expected utility maximization and their own computation of the result of all their actions, and the outcome that is going to result because of the rationality and the intelligence of the players is called an equilibrium. And this notion of an equilibrium was formalized by John Nash. and it gets the name Nash equilibrium for this reason. So, okay, so that is a very simple game that I gave you. Now you can also define a game underlying the Vickrey auction that I showed you earlier. I will not get into the details of this. This slide only shows that whatever is happening in an auction can also be very faithfully captured using a strategic form game. Of course, I have to say something about John Nash. All of you would have seen this beautiful picture called Beautiful Mind. And John Nash, he was born in 1928, and at the age of 20, he got his MS, and then he got his PhD in Princeton University in the 1950s. And his PhD thesis is just 28 pages. You can actually go to the web and download his PhD thesis and then take a look at it. And he had two absolutely astounding results in this thesis. The first result was to establish the existence of a mixed strategy Nash equilibrium in all finite strategic form games. That was the first result. The second result is on what is called Nash bargaining theorem, which means that if there are two persons who are bargaining for something, what is the optimal solution there? He was able to prove, using an axiomatic approach, the existence of a unique solution for the bargaining problem. And in 1994, he was awarded the Nobel Prize along with Zelton and John Harsanyi for analyzing the equilibrium behavior of games. And his life is a very fascinating piece of, so many of you would have seen the picture, and you should actually read his biography and so on. Nash was the one who formalized the notion of an equilibrium. So he said that a Nash equilibrium is a combination of strategies of the players, that is one strategy for each player, which is such that in the equilibrium, it is always good for the player to stick to the equilibrium strategy, assuming that the other players are also sticking to their equilibrium strategies. So each player, assuming that the other players will be sticking to their equilibrium strategy, it is always good for the player to stick to the equilibrium strategy. So there is no point in deviating from this equilibrium strategy. So such a combination, such a profile of strategies would be called as a Nash equilibrium. And it turns out that it captures a very stable, self-enforcing agreement among the players. In other words, what it means is that if you recommend a Nash equilibrium strategy to each one of the players, then the players are in some sense very happy. They don't have to deviate from the Nash equilibrium strategy that is suggested to them. And only thing is, if the other players deviate, then you will not be able to say anything about the happiness of the each of the players. Okay, so in the case of the IISc MG Road example, one Nash equilibrium certainly is IISc, IISc. It's actually a Pareto optimal Nash equilibrium. The other Nash equilibrium happens to be MG Road, MG Road. Whereas what John Nash was able to show is that for such games, there is also another Nash equilibrium called the mixed strategy Nash equilibrium, where you are not playing just one strategy or a pure strategy. You're actually playing a mixed strategy, which means a probability distribution among those strategies. For example, you may play IISc with probability 0.8 and MG Road with probability 0.2, according to a probability distribution. And he showed that this particular game has a Nash equilibrium, mixed strategy Nash equilibrium, which says that 1 by 11, with probability 1 by 11, you will play IISc, and with probability 10 by 11, you will play MG Road. That is 10 by 11 times you're actually in MG Road, and only 1 by 11 times you're in IISc. So if you play your strategies according to this probability distribution, then John Nash actually showed that this will be a mixed strategy Nash equilibrium. So this explains why most of the IISc students are actually on MG Road and not in IISc, because that provides a Nash equilibrium for them. So I have already told you the significance and relevance of Nash equilibrium. It's a stable, self-enforcing, self-sustaining agreement. And if a referee or a third party goes ahead and then recommends a Nash equilibrium strategy for each player, then there is no need for the players to deviate from that. If all of them stick to their Nash equilibrium strategies, they are kept very happy. So that is why it is called an equilibrium. So when you have a strategic form game, game theory basically tells you how to analyze the equilibrium behavior of these games, how to compute all the Nash equilibria of this game, because this is what you would expect the game to result in when the game is played repeatedly. Okay. So this is the most important result in game theory. So at the end of this talk, if one of the takeaways would be the following. If somebody asks you the question, what is Nash famous for? So this is the Nash existence theorem. It says that every finite strategic form game has at least one mixed strategy Nash equilibrium. So he settled the question of existence of a mixed strategy Nash equilibrium once and for all. He said, if the game has finite number of players and each player has finite number of strategies, then such a game is definitely going to have at least one mixed strategy Nash equilibrium. So this is the famous Nash theorem, which is like the cornerstone for game theory and mechanism design. So this is one takeaway from this talk. Now, it turns out that in 1994, as I already told you, John Nash, Zelton, and Harshiani got the Nobel Prize in economics. In 1996, this economics Nobel Prize was won by William Vickrey for discovering Vickrey auction. And then ever since 2005, a string of Nobel Prize awardees are there in this area. 2005, Robert Aumann and Thomas Schelling, they actually got the Nobel Prize in Economic Sciences. Robert Aumann actually visited the Indian Institute of Science in 2006. Then Harvick's Eric Maskin and Roger Myerson got the Nobel Prize in 2007. Eric Maskin visited the IISc during the IISc centenary in 2009 and gave a talk. And I'm very fortunate to have Eric Maskin writing a foreword to my book on game theory and mechanism design. And then Lloyd Shapley and Alvin Roth got the Nobel Prize for their work on matching markets. This was in 2012. And the most recent Nobel Prize also has gone to game theorists, Paul Milgrom and Robert Wilson from the Stanford University, for their seminal work on spectrum auctions. So you can see that both game theory and mechanism design have seen living legends getting Nobel Prizes. And this is one of the reasons why this is an area which is so exciting and with lively action going on all over the world. Okay, so now let me come to mechanism design. So mechanism design can be considered as the reverse engineering of games. So what does mechanism design do? It designs a game. It designs a game in the following way. It actually induces a game among the players such that in some equilibrium of the game, because you know that a game is bound to reach an equilibrium if one exists, and then in some equilibrium of the game, a desired social goal or a social choice function gets implemented. So what you are trying to do is, just as the Indian cricket team designed a mechanism with which they were able to actually win the 4th test by scoring those 327 runs on the final day. There was strategy involved there. So what they have done is they came up with strategies so that when the opposing team applies their strategies, they had their world-class bowlers, but the strategy was very, very clear. So with a very clear strategy, they were able to sort of induce a game among the 11 players of Australia and 11 players of India in a way that the final outcome was in India's favor. So this is what mechanism design is all about. There is a desired social choice function. In the case of the cricket match, it is India who are trying to win here, and then Australia loses. So it's a zero-sum game. But games need not be zero-sum games. Games can involve stakeholders, and all the stakeholders, can be utopian, meaning, all of them are good people, and we would like to do good for everybody. So what you are basically trying to do is you will define a social choice function, which will in some sense capture the aspirations of all the players, and you will try to maximize the sum of all aspirations of all the players. So this is what is called social welfare maximization. So if you want to do social welfare maximization and make the game win-win, then can you design a mechanism which, in spite of the self-interested behavior of the rational and intelligent players of the game, still ensures that a socially optimal outcome will result, is what mechanism design is all about. So coming back to the cake cutting problem, what is the mechanism that the mother designs here? It's a beautiful mechanism, very simple to understand. What the mechanism designer mother does is gives the knife to one of the kids and tells the kid, you now slice the cake into 2 portions, and tells the second kid, now once it is sliced into 2 portions, tells the second kid, you will now get the chance to pick up one of these 2 slices. So now this is a mechanism. What you have done is by defining a game here, what you are now doing is you are now making the 2 kids to play a game. So what's the game here? So in this game, the kid is now kid 1 is slicing the cake, and kid 2 is now picking up one of the portions. What does kid 1 do? Now kid 1 knows that kid 2 is going to pick up the larger of the 2 portions. So what the kid 1 will do is to slice the cake into exactly 2 halves, as exactly as possible, so that when the kid 2 picks up what she thinks is the larger of the 2 portions, the kid 2 is getting exactly half only. So now, once the kid finishes the slicing of this cake, what the kid 2 will do is to look at these 2 slices, and she will pick up what she thinks is the larger of the 2 slices. So here is a situation where kid 1 is happy, Tamil Nadu is happy, kid 2 is happy, Karnataka is happy, and also Narendra Modi is happy. So here is a very simple mechanism. It may look to be very innocuous. This problem has very significant implications for many burning problems that we have. So if a proper game formulation is done and mechanism design is applied, there is no reason why a satisfactory solution cannot be found. Coming to the Vickrey auction game. So as I told you, what Vickrey came up with was a remarkable observation that the highest bidder will pay not whatever he has bid, but will pay whatever the second highest bidder has bid. So in this particular case, 40, 45, 60, 80 are the 4 bids. Now agent 4 will win the auction, but will not pay 80, but will pay 60. So because the agent knows that he is going to pay something lower than what he has bid, he will try to bid as aggressively as possible. And Vickrey showed a remarkable thing. He showed that if you have a valuation for an object, for example, let us say you are trying to buy a camera, and your valuation for the camera is 1,000 rupees. So if you are participating in an auction for this camera, typically your tendency will not be to bid 1,000, because 1,000 is your valuation, but you will bid 700 or 600 because Because what you want to do is, if you are able to get it at 700, then your utility is 1000 minus 700, because 1000 was your valuation, 700 is what you are paying. So your utility is actually 300. So what you want to do is, you want to do utility maximization here. But Vickrey came up with a fantastic scheme where if your valuation is 1000, you will actually bid 1000. You will not bid 700 or 600. You will bid 1000, because you know that you are going to pay something less than what you have bid. And by showing that by bidding second highest bid, Vickrey showed, using a very deep game theoretic formulation of the problem, that it is a best response strategy for you to bid your own true valuation in order to attain what is called as a dominant strategy equilibrium here. So this is very similar to saying Satyameva Jayate. That is, whatever the other players are going to bid, your best strategy is always to tell the truth. That is, the report your true valuation. So this principle of Satyameva Jayate is beautifully achieved by the Vickrey auction game, and you're able to show using game theory and mechanism design that this is indeed true. And indeed, Vickrey auction turns out to be a fundamental building block of most of the auctions, high value auctions, which are getting designed for various items, including the spectrum auction and so on. Okay, so I do not have the time to show that Vickrey auction is actually truthful. So the slides are going to be made available to you. Just take a look at this proof, which shows that bidding true valuation is actually the best strategy for you. Okay, so now I think we have an understanding of mechanism design. Mechanism design is all about designing a game with a desirable behavior. This desirable behavior can take several forms. One is called the dominant strategy incentive compatibility, Bayesian-Nash incentive compatibility. These are truthfulness of different degrees. Then allocative efficiency, you want to give the objects to the people who value them most. Budget balance, you want to balance the budget between the buyers and sellers. Non-dictatorship, you don't want the allocation to be biased. Then individually rational, you don't want the stakeholders to lose their money. So these are some desirable properties that social choice functions that you want to implement using your mechanisms to satisfy. But unfortunately, not all of them can be satisfied at the same time. It turns out that the goal of mechanism design is to satisfy as many of these properties as possible, as maximal combination of these properties as possible. And this is what has led to very remarkable results in mechanism design theory over 5 to 6 decades now. So there is a host of impossibility theorems and possibility theorems, and to capture the intricacies involved here, it turns out that if you're looking at the space of all mechanisms, that could be a very large space. BIC actually stands for Bayesian incentive compatible, but don't worry about these acronyms right now. Now, it turns out that there is another subclass of mechanisms which satisfy very strong properties. Now, if you want these mechanisms to satisfy another property called allocative efficiency, so the space of mechanisms now shrinks. And then if you want another property called weak budget balance to be satisfied, the space of possible mechanisms will shrink further. And then there is a property called strong budget balance, which will now eliminate many other mechanisms from contention. And then there is a property called exposed efficiency, which will make things even more complicated. And then there is a property called individual rationality, which will again complicate the space of mechanisms. And then you have several other mechanisms and properties, and you will see that what you have is a maze of possibilities. Now, mechanism design is all about figuring out what is the combination of properties you want your social choice function to satisfy, and try and see whether you are able to design a mechanism which will satisfy these. So you are aided in this exercise by a host of possibility and impossibility theorems, and this becomes a very technical subject. And this is where game theory and mechanism design turn out to be intellectually very, very exciting topics to study. Okay, so let me just tell you how mechanism design can be used for a variety of applications, including policy making. Now, here is a situation where what we want to do is to come up with policies for the government, which will ensure that the farmers are benefited to the maximum extent possible. So you have all these agricultural heat maps for the country. So there's enormous amount of data available about agricultural production in the different states. So what is shown in the middle are some typical heat maps. Now these heat maps can be regarded as a Nash equilibrium of an underlying game. So what we have defined here is what is called as a heat map game. What is the heat map game? This is a very high level game that you are talking about. The heat map game basically is a Nash equilibrium of a game that captures all the government policies, all the behavioral dynamics of the farmers at an aggregated level. And so when you do a game theoretic analysis, you know that the existing heat map of the country happens to be a Nash equilibrium of the current game that involves the government, the farmers, and a wide variety of other stakeholders who are in the agricultural sector in the country. And now what we want to do is, let us say you're able to picture a more desirable heat map, agricultural heat map for the country. So that's a more desirable equilibrium. So now the question is, if you know what a desirable Nash equilibrium for the country is, you will now be able to come up with a mechanism or policies of the government which will be able to drive the country towards a more desirable Nash equilibrium. And in trying to achieve this, mechanism design can play an extremely important role. So designing a game, having a desirable heat map as an equilibrium is going to be an exciting research direction that we want to pursue at the Game Theory Lab at IISc. So let me conclude with this. Let me say that, the subject of game theory is the science behind microeconomics. And it is a fantastic tool for solving strategic problems at the interface of computer science and economics. And that is, game theory deals with analysis. Whereas what is mechanism design? It is the reverse engineering of games. And we have seen that it can be used in a variety of societal applications. And, agriculture, healthcare, education, transportation, policy making, conflict resolution in general, they're all waiting for game theory and mechanism design to be applied. In fact, indeed, they have already been applied, and there are many rich problems that will benefit from a scientific application of game theory and mechanism design. So with this, I will conclude, and will be happy to take any questions. And I don't have to answer those questions now. All that you have to do is to buy my book on game theory and mechanism design. You will have answers for all those questions. If you're not familiar with English, but you're familiar with only Chinese, then there's a Chinese version of the book on game theory and mechanism design. I would encourage you to read the Chinese version of the book as well. Thank you very much. Thank you for this wonderful opportunity, Professor Murthy, and I wish all the best to BITES. Thank you.
Thank you so much, sir. It was very nice, like the way it is, MG Road is for IISc, the Nash equilibrium. For the DSU students, it is Forum Mall.
Okay. Okay, very
So
good.
I now request our Dean, Dr. A. Srinivas, sir, to propose the vote of thanks.
Srinivasan, are you around?
Imtiaz, sir, please make Srinivas, sir, co-host.
Yeah. Yes, sir. I'm audible, sir.
Yes, yes, yes.
Yes, sir. Sir, it was a very intellectually stimulating talk, and our students and faculty have been longing to hear to you, sir. And it was a great occasion this morning to hear from you. It was a very, very interesting experience. Normally, our students most of the times think computer science is programming, but there is so much of connection between logic and mathematical modeling, and the things like the social welfare maximization, and the Vickrey auction that you were talking about, the bidding. Even I was thinking if it could be applied to the bandwidth bidding by the telecom providers. So in all, I think it was a very satisfying experience for us to listen to you, sir. We were really longing to meet you for a long time. And thank you so much for your time. I am very sure our students have got really stimulated by the kind of rigor that is needed for computer science studies. So again, thank you, sir, and we look forward to many more talks from you on such topics. Thank you, sir.
Yeah, thank you very much. Thank you very much. Namaste to all of you. And please feel free to send me email at narahari@iasc.ac.in. Please take a look at my website also. And, for any questions, do contact me. Thank you so much.
Thank you, sir. Thank you, sir.
Thank you so much.
Professor Murthy here. I think I request you to consider giving one more talk at a later date when you're.
We'll be happy to. So if we are able to make enough progress on our digital agricultural research using the mechanism design, we'll be very happy to give that talk.
Yes, yes, sir. Thank you, sir. Thank you very much.
So nice of you, sir. Thank you.
Thank you.
World-class faculty, brilliant credentials from the best universities.